Hello students, welcome to EPG Pathshala. I am Dr. Rajiv Jain, Professor of Chemistry at Jivaji University, Gwalior. Today I shall speak on types of instrumental methods under the paper Fundamentals of Analytical Chemistry. Learning objectives of today's lecture is that what are analytical instruments, how they are used, what is their purpose, how they can be applied for the analysis of different types of substances. So students, if you consider, you have heard the quality of a substance. What is the quality of a substance? You want to determine quality of the substance, how the quality of a substance can be determined, what type of substances are present in the given material, what is the amount of substances in the given material. All these things constitute the quality. Today it is great emphasis is there on the quality of a given material. You must have seen on every product which you purchase from the market, whether it is some cosmetic, whether it is some pharmaceutical, it is a drug or any other material, it is mentioned on that what is the percentage of each and every component of the material. So for that purpose, analytical chemist is needed to analyze qualitatively as well as quantitatively different components of the material which is given to us. First we do qualitative analysis, means to find out the quality of the substance, what type of components or substances are present in the given material, and then we want to know the amount of substances present in the given material. The amount, if we say that if limit exceeds, then the substance is toxic to us. If limit is not exceeding, then it is good. For example, if we are analyzing water sample, we say that if the component of a given material is less than 0.01%, then we will say that the quality of water is good. It can be used for that purpose. If its quality is that exceeds 0.01%, then we will say that quality is not good. So for that purpose, we may use classical methods of analysis or we may use instrumental methods of analysis. Different types of methods are available. In classical methods, we have volumetric and gravimetric analysis, and in instrumental method, we have number of instruments which I shall discuss in today's lecture. The analytical chemist is concerned with different methods of analysis. Analytical chemist must be familiar with the theoretical principles and instrumentation of all methods. He seeks to improve methods, searches for new areas of application, and points out the limitations so that the technique will not be misused. Accuracy, precision, reproducibility, and reliability are everyday words which an analytical chemist uses. In a real sense, the analytical chemist is the keeper of chemistry's tools and techniques. In the present lecture, I am introducing you some of the analytical methods which all chemistry students will use in the more specialized branches of chemistry. From the following paragraphs, it will be clear how by understanding few principles of chemistry, various techniques can be easily appreciated. It will be of interest to students to understand that how these techniques are interrelated and simple to learn. Concepts can be explained by taking few illustrations. For example, melting process involves a two-phase system and is best understood from a study of phase diagram. Similar principles apply to distillation, a somewhat more sophisticated separation technique where the concept of column process is introduced. In distillation, there is a distribution of material between a gas phase and a liquid phase, whereas in extraction, there is a distribution of material between two immiscible liquid phases. In extraction, we develop the concept of a distribution coefficient which describes how a component is distributed between two phases. The concepts of distribution and flow through columns from the basic framework for chromatographic methods in which a complex mixture is separated into its components by selective retardation as the sample is washed through a packed column or over a specially prepared paper surface. Chromatographic methods include some of the most powerful and useful separation techniques. You may consider the substance which is given to you. It may be a material in a test tube, it may be water, it may be solid, it may be gas. Then you cannot tell me, if I give you water in a test tube, you cannot tell me that this substance is water. So you may consider that material and test tube as a black box. That something is there in the black box. How to identify the substance present in that black box is a very important thing. For that, different types of instruments are used. One of the simplest method is that you heat the test tube and you find out the boiling point. If the boiling point is 100, then you will say that the substance may be water. Or in other words, I can say that you have to perturb the system, you have to excite the system, you have to provide the energy so that something comes out. For example, here you have seen that by heating it. But if you are doing some instrumental analysis, then you have to pass through electromagnetic radiation. When you pass through electromagnetic radiation, then the technique is called spectrophotometry, and you observe the absorption or emission of the electromagnetic radiation by the substance present in your test tube. On the basis of how much amount of the substance has been absorbed by the your given material, your substance in the test tube, you may say that this absorbance is proportional to concentration. By applying Beer's law, you can find out the concentration of unknown substance. Similarly, various other instrumental methods are there. If you apply certain types of potential there, you pass certain types of electromotive force and then you observe the current. You are applying potential and you are observing the current. It means you are equalizing the current with the concentration of unknown substance. Then this is the another method. Or in another method, there are thermal methods where you will apply heat and you will observe the effect of heat on that substance. What is the effect of heat on that substance? That will be called as thermal analysis, or you will call them differential thermal analysis, thermogravimetric analysis, differential scanning calorimetry. Then another type of techniques are radiometric analysis. That is, in radiometric analysis, you are using different types of radioisotopes. In today's world, there is much importance is given to radiometric methods, because by using carbon dating, you can find out different constituents of a substance. This is the ultimate analysis. So I mean to say here that for finding out or for analyzing the unknown substance, you cannot analyze it by just seeing the substance, but you have perturbed the system, and that can be done by applying some source of energy. It may be heat, it may be electromagnetic radiation, it may be in the form of potential absorbance by the solution present in your system. So different types of analytical techniques, instrumental techniques are divided in this way. In second category, the study of the interaction of electromagnetic radiation with matter is the basis for different spectroscopic methods. At one end of the spectrum, Y rays and X-rays provide us the information about nuclear, atomic, and molecular structure. Whereas on the other extreme of the spectrum, there is relatively low energy radiations in the radio frequency range. These low level frequencies are of common concern to communication scientists and engineers, but in combination with an intense magnetic field, this type of energy can interact with certain nuclei, giving us a very useful and powerful technique known as nuclear magnetic resonance. In between frequencies are ultraviolet and infrared radiations, both having capabilities of providing information about the nature of atoms, ions, and molecules. The well-known region of the spectrum is visible radiation, which is in between the ultraviolet and infrared region. While the inorganic and organic chemist may use visible radiation to study the structure and stability of transition metal complexes and organic molecule, the layman may use it for a simple determination of the strength of the colored solution, as by simply observing the different colors, one may see which solution is concentrated and which solution is dilute. Most spectroscopic methods, the sample is exposed to one or the other type of radiation, whereas in mass spectrometry, the sample is bombarded with a beam of electrons which ionizes the molecule into many pieces. The spectrometer sorts the electrically charged fragments in order of their mass to charge ratios. The third category is the classical study of chemical equilibria. Stoichiometry and equilibria are the basis of gravimetric, titrimetric, and electrometric analytical techniques. It includes the elementary concepts to more complex systems involving the study of electrode reactions under controlled experimental conditions and the use of solvents other than water. The next class of analytical methods include radiochemical techniques, which are gaining importance due to requirements of energy sources. For many analytical problems, the use of radioactive isotopes provides the ultimate in trace analysis. The last topic involves the study of concepts used in the operation of a large-scale commercial or scientific analytical laboratory. To a great extent, automation has replaced the routine analysis. At the push of a button, man-made devices can weigh a sample, dissolve it, add reagents, mix and filter, heat or cool it, titrate it, or measure its absorbance and print the results. Process analyzers give an immediate and continuous monitoring of a chemical process. Such information entered into a feedback loop can control the operation of an entire plant. In this lecture, my objective is to present basic principles and concepts which underlie most of the instruments and techniques in use. In the next 10 years, we will see a spectacular change in the types of analytical methods used routinely and the kind of information they are able to reveal and unfold various intricacies. Given a sound background, the student will be better prepared and more capable of understanding. Our study of chemical analysis begins with one of the earliest observations that substances melt and boil at particular temperatures, and in so doing, change in form from a solid to a liquid, or from a liquid to a gas, or the reverse. The transitions between these states of matter or phases provide information which helps to identify the substance and determine its purity. Furthermore, since the mechanical separation of two phases is relatively straightforward, a study of the distribution of a component between two phases provides the basis for all separation techniques. The phase change represented below may occur with either a single pure component or element or a mixture of two or more substances. Solid liquid equilibrium. When a solid sample is heated, its temperature rises as shown in figure. At a characteristic temperature, the solid begins to melt and there is a discontinuity in the heating curve. If the heating is continued, the solid continues to melt at a constant temperature known as the melting point. The additional heat is absorbed as latent heat of fusion, which is the energy required to disrupt the crystal lattice. When the solid is completely melted, the temperature of the liquid begins to rise again, but usually not at the same rate as for the solid because the heat capacity of the liquid differs from that of the solid. It has been assumed that during phase transition the system is well mixed so that an equilibrium is maintained as shown. If we reverse the process just described and cool a pure liquid, we obtained a cooling curve that is not quite a mirror image of the heating curve. As shown in figure, the temperature may fall below the equilibrium freezing point before the first crystal appear, a phenomenon known as supercooling. The extent of supercooling varies with the nature of the substance, the rate of cooling. The extent of supercooling also depends on mechanical actions such as stirring and vibrations, and with the presence of impurities which can act as nuclei in the formation of the crystals. The melting point of a pure solid is always sharp except for liquid crystals and serves to identify it. If the absorbance is not pure, it will melt over a range of temperature. The change in volume on melting or freezing is relatively small. Therefore, the effect of pressure is almost always negligible. Melting points are often determined in the very simple apparatus as shown in figure. The sample contained in a thin-walled capillary and the thermometer should be in close proximity and heated at a rate not exceeding 1 degree per minute as the melting point is approached. More sophisticated apparatus are also available for increased accuracy, speed, and convenience. There are several sources of error in this determination, some of which are easily corrected. Adequate heat transfer must be provided by using a well-stirred bath, a thin-walled capillary, and a very slow heating rate in the region of the melting point. If the bath temperature is well above room temperature, a thermometer correction may be necessary to allow for the variation in the density of mercury along the export column. Liquid gas equilibrium. All molecules in a liquid are in constant motion, thus generating an internal pressure and a tendency to escape from the liquid. The vapor pressure of a liquid is a measure of this escaping tendency and is the pressure that would be observed in the vapor phase if the pure liquid is placed in an evacuated chamber and allowed to come to equilibrium. If the chamber also contains another gas, the total pressure includes the vapor pressure of the liquid, and we speak of the partial pressure of each component. The vapor pressure of the liquid is a property of the liquid and does not depend on the composition of the vapor phase in contact with it. Because vapor pressure is the result of molecular motions, we would expect it to increase with an increase in temperature. Figure shows how the vapor pressure of a typical liquid changes with temperature. If the vapor pressure is equal to or greater than the external pressure, the liquid will boil as fast as the latent heat of vaporization. The temperature at which the vapor pressure is 1 atmosphere is the normal boiling point. However, the boiling point at any pressure is given by the curve as shown in figure. This curve also separates two regions, any combination of external pressure and temperature to the left of the line. Example point A is in a region in which the liquid phase is the stable form. Point C is in a region where the gas phase is the stable form. Point B and other points on the line give the only condition for which the two phases can coexist in equilibrium. Solid gas equilibrium. The escaping tendency of a molecule in a solid is usually very low compared to a liquid. Nevertheless, a vapor pressure does exist and it depends on temperature in the same manner as the Capillion equation. Phase diagram. It is convenient to summarize the three types of phase transitions in a single graph called a phase diagram. As a familiar example, the phase diagram for water is given in figure. Curve A separating the regions in which the solid and vapor are stable gives the vapor pressure of the solid as a function of temperature. If the pressure above the solid is less than this, the solid will sublime. If the pressure is greater, the vapor will condense. Similarly, curve B between the liquid and vapor regions depicts the vapor pressure of the liquid as a function of temperature. The dashed portion of this line, curve D, gives the vapor pressure of the supercooled liquid if it exists. Curve C shows the melting point as a function of pressure. It is very nearly a vertical line with a negative slope because water expands slightly on freezing. For a given temperature and pressure, the phase diagram indicates which phase will exist at equilibrium. If a particular combination of pressure and temperature lies on a curve, two phases will coexist in equilibrium. There is one unique combination where the curves intersect the triple point at which all three phases can coexist. So, in this lecture, you have studied that how a given substance can be qualitatively and quantitatively analyzed, how the quality of a substance can be determined. For example, if I am going to synthesize a drug in bulk, tons of drugs will be synthesized. Then at each and every step, suppose it involves 10 steps or 12 steps, or synthesis involves 8 steps, then at every step I have to find out the purity of that substance. How to find out the purity of that substance? Purity means to analyze different types of substances present in that material which I have synthesized. So that can be easily determined by different types of instruments used. So that is the parameter where at each and every step, analytical chemistry is required. If some process instruments is there, process instruments is there, is that if in some industry, some process is going on, some reactors are being used for the preparation of different types of fabrics, different types of materials, that at each and every step, I have to apply different analytical methods. And these analytical methods are in this way that automatically the substance which is synthesized automatically go to the automatically analyzed. For example, I have synthesized some material, I want to find out its purity. Automatically it go to your chromatograph, where chromatograph tells us whether this material contains one component or two component or three component. If it contains more than one component, it means impurities are there. Then again, organic chemist will remove the impurities, and again it will send to the chromatograph. Uh, then analytical chemist will say now the material is pure. And then second step will come, and after second step it may go to some ultraviolet spectrophotometer or IR spectrophotometer, or nuclear devices may be used for that purpose to identify whether the desired compound has been formed or not. Once analytical chemists say that the desired compound has been formed, then it will go to the next step. So it saves our time and energy. It saves both time, energy, and cost, because at every step we are assuring ourselves that the compound which we are preparing is 100% pure. After that, we are proceeding. In this way, at every step, we are maintaining the quality from reagents to products. We are maintaining the quality. That is the role of analytical chemist, and that is the role of different types of instrumental methods available in the hands of analytical chemist.